Hello and welcome to this video tutorial on how to find subintervals of increase and decrease, a local extrema, and points of inflection of a function. So let's take a look at our question. Let's begin with part 1. Now, when asked to find the subintervals of increase and decrease of a function, you are being asked to find the intervals where the curve is increasing, i.e. when the slope of the tangent to the curve is positive, and the intervals where the curve is decreasing, i.e. when the slope of the tangent to the curve is negative. So we begin by getting the first derivative of the function. Using basic principles of differentiation, we multiply the minus x cubed by its power of 3, while reducing this power by 1. We then multiply the 6x squared by its power of 2, while also reducing this power by 1. We do the same to the x value, and this just turns the x into x to the power of 0, which, as we know, for any number is 1. So this gives us our first derivative of minus 3x squared plus 12x plus 135. We now let this equal to 0 to find our x values. Factorize first if possible, and this now leaves us with x equal to minus 5 and x equal to 9. Now we need to sub in a number smaller than minus 5, a number between minus 5 and 9, and a number larger than 9 into the derivative to find out if the curve is increasing or decreasing. If our corresponding result is greater than 0, then the curve is increasing in that interval. If it is less than 0, then it is decreasing in that interval. So we will test minus 10, 0, and 10. For minus 10, we get out minus 285, which is less than 0, so the curve is decreasing from negative infinity to minus 5. For 0, we get out 135, which is greater than 0, so the curve is increasing from minus 5 to 9. For 10, we get out minus 45, which is less than 0, so the curve is decreasing from 9 to infinity. So these are our subintervals of increase and decrease, and the answer to part 1. Now on to part 2. So finding the local extrema of a function is really finding the highest and or lowest points of the curve. To find these points, we let the first derivative equal to 0 and solve for x. Now, as we've already done this in part 1, we know that this gives us local extrema occurring at x equal to minus 5 and x equal to 9. We sub these values into our original equation to get the corresponding y values at these points. This gives local extrema at minus 5, minus 400, and 9, 972. Now we plot the graph of the function to verify the local extremes, and we can see clearly that the two local extremes do in fact occur at these points. Now on to the final part of this question. So the concavity of the function is really asking you what the general shape of the curve is. So we'll begin by finding our point of inflection. To find points of inflection, we differentiate the function twice and let the second derivative equal 0. So as you can see here, we solve for x to find x equal to 2. This is the x value of our point of inflection. Sub this x equal to 0 into the original equation to find the corresponding y value, and you can see that we get y is equal to 286. So our point of inflection is 286. To determine the concavity of the function, we are going to sub in a number smaller than x equal to 2 and bigger than x equal to 2 into our second derivative. So we'll choose 3 and 0. When we sub in 3, we get out minus 6, which tells us the second derivative is negative when x is equal to 3. When we sub in 0, we get out 12, which means the second derivative is positive when x is equal to 0. So as you can see in this graph, the function is concave up for all values of x is less than 2, and is concave down for all values of x greater than 2. So that brings us to the end of the question and to the end of this video. Thanks for watching, and I hope this video helped you with any problems that you've been having.